Thank you for joining me. I'm Ivan Schuller from the Physics Department at the University of California in San Diego. My guest today is Professor Walter Kohn, the 1998 winner of the Nobel Prize in Chemistry. Welcome, Professor Kohn.
Thank you very much, Ivan.
How is it coming back here to UCSD, since you're an all-timer here?
Absolutely wonderful. I heard you introduce me as a guest, and I feel very happy as a guest here, but actually I feel at home here, because, and not so much as a guest, because I came here just about 40 years ago, not quite, at the very beginning of the university, and I spent 20 years here, so it's really home for me.
So it's a real pleasure for us to have you here. So you were in the physics department at UCSD. However, you won the Nobel Prize in Chemistry. How does this work? How does a physicist win a Nobel Prize in Chemistry?
Well, it is a bit curious, and it doesn't happen all that often. After it became known that I won the Nobel Prize in Chemistry, much to the surprise of all my physics friends, a friend of mine, a historian of science, told me a story. There's a precedent, namely Lord Rutherford, a New Zealander, a very famous physicist who did some of the very early work on radioactivity, including transmutation of elements. And when he was told that he won the Nobel Prize in Chemistry, he said, well, I've transmuted quite a few elements in my life, but that doesn't compare to what the Swedish Academy did for me. They transmuted me from a physicist to a chemist. So I felt a little bit the same way.
But it was expected, of course, either in chemistry or in physics. So now there is a chance to get it in physics also.
Well, yeah, that chance is much less than that of the proverbial snowball in hell. But in some other sense, I already got it in physics, because after the announcement of my Nobel Prize, I got a letter, very strange envelope that I couldn't really quite figure out where it was from. It was a registered letter. I had to go to the post office to pick it up. It turned out to be from the Dalai Lama in India, a gentleman whom I admire enormously and whom I know slightly. And somehow word got to him that I won the Nobel Prize, and he sent me this very nice congratulatory letter congratulating me on winning the Nobel Prize in Physics. So now I think if I have a Nobel Prize in Physics from the Dalai Lama, I don't need it anymore from the Swedish Academy.
Oh, you shouldn't have said that, maybe. That you don't. So how is, actually this brings me to an interesting question. How has your life changed? You know, you were for a while a professor of physics in Santa Barbara, and now suddenly you're one of our big heroes.
Chemistry heroes, right?
Chemistry
heroes. So my life actually sort of began to change something like a decade ago when chemists became more and more interested in the work that I've been associated with and for which I was awarded the prize. So that was one change. I began to attend perhaps as many meetings of theoretical chemists as physics meetings. Now, since the prize was awarded, yes, that's a big change. The absolutely most wonderful thing about the prize has been the fact that this becomes known worldwide, and so I have, as a result of that fact, I've heard from dozens of people that I had considered long lost that suddenly heard, hey, this man won the Nobel Prize, I know him, and who got in touch with me. So that's been the best part, and I've been very busy picking up these old, new acquaintances.
So you received the Nobel Prize for the development of density functional theory. Can you somehow tell us, I mean, I guess maybe some kind of a explanation of what this density functional theory is? How does this relate to the electric nature of matter?
Okay, I'll try. And I hope I manage reasonably well. People who have had a course in chemistry may remember that they've seen pictures in their high school textbooks or in their college textbooks of atoms. Let's take the hydrogen atom, it's the simplest one. And you would expect, if you know a little chemistry, the atom is a nucleus and an electron, and you would expect that the nucleus is pretty small, so it looks like a small sphere, and the electron is a little bigger, but still a very small sphere. So you'd sort of visualize one particle, the nucleus, and another particle, the electron.
Forgive me for interrupting you, but do you think of this in these actual terms as a Nobel Prize in chemistry, or you actually think of this more in complicated equations, or do you actually think with these pictures, nucleus, positive, electron, tiny little sphere?
Yes, absolutely. I do think in pictures, but no, not that picture. That was the previous picture. Okay. The nucleus is a little sphere, and the electron is still a little sphere, although bigger than the nucleus. That's the old picture that goes back to Niels Bohr, and the picture that he had of the hydrogen atom was the nucleus is very heavy, and so essentially doesn't move, and the electron is a little particle, and it goes around the nucleus pretty much like the Earth goes around the sun, or the moon goes around the Earth. And that was a very good model, and it explained many things in a remarkable way. But it was the beginning. Later, there was a major step forward taken by an Austrian physicist by the name of Schrödinger. It's a bit of a tongue twister for English-speaking people. And so he had a quite different picture of the hydrogen atom. His picture was still that the nucleus is pretty much a particle, it doesn't move much, stays put, but the electron, instead of being, again, a particle going around like a planet, was described as a wave going around. That's a little hard to visualize.
Maybe like a cloud?
No. Now I come to the cloud.
Okay.
So with Schrödinger, it was not a cloud, it was a wave, like a water wave that's going around the nucleus. Now, the picture of a cloud was introduced later, and that's probably what you've seen in your books. You've probably seen a picture of a hydrogen atom as a nucleus in the middle, and then there's an electron cloud spread around it. It's rather dense near the nucleus, and it becomes less and less dense, and the density just fades away. So if you've seen that kind of a picture, then I come back to the question you asked me, what is this density functional theory? The density that I'm talking about is the density of this cloud. Now, to go a little further to explain what my contribution has been, and I shouldn't say my, because I've, of course, worked with other people, and many other people have contributed to this independently of me. Let's say rather our contribution has been. It used to be thought that this picture of the electrons as a cloud was a very rough and fuzzy description of the reality, of the quantitative reality. And basically what we showed was that we could reformulate the older existing theories, for example, this wave theory of Schrödinger. We could formulate it entirely and completely in terms of this cloud picture, and mathematically speaking, precisely and rigorously. And that was something new, and it opened up a new perspective on the structure of atoms, of molecules, and of solids. The density that occurs in the expression density functional theory is the density of the electrons.
I see. And what it is good for?
Yes.
I'm not asking you actually an applied question. Let me just make clear in these talks we try to kind of distinguish basic research from real applications, which is where it's confused in the common. What it is good for, I mean, in the basic research.
Scientifically.
Scientifically, yes.
Yes. That can be very simply expressed. I think the main utility of this has been the following. Traditional methods, theoretical methods of understanding, let's say, molecules, have been based on this Schrödinger wave picture. And they are phenomenally successful as long as you deal with relatively small structures, structures like the water, an isolated water molecule, or some more complicated molecule. But once you get about structures containing more than about 10 or a dozen atoms, these traditional methods just can't handle it anymore. And if you want to deal with a molecule that has 20 atoms, the theoretical task to describe that may be 1,000,000 times harder than a molecule of 10 atoms. So pretty soon you just can't go any further. So traditional methods have been limited to understanding relatively small structures. They have been phenomenally successful. Density functional theory has broken that barrier, and with density functional theory, some of my friends and colleagues have been able to deal with structures including 100, even up to 1,000 atoms. So that opens up a whole new field of chemistry and physics. For example, most organic materials contain way above
Carbon 60.
10 atoms. Carbon 60 is an example. In fact, in my talk this afternoon, I will show a picture of carbon 60, which is a wonderful kind of molecule, almost spherical, consisting of 60 carbon atoms beautifully arranged around the sphere. And what I will discuss is something calculated with density functional theory, where you have such a molecule of carbon 60, and inside, since it's a kind of an empty cage, you have some other atom. And we can now calculate with density functional theory how this other atom moves around.
You mentioned Schrödinger's name, and you mentioned actually something that I wasn't quite aware of, that Schrödinger was Austrian. And you were born in Austria as well. And actually, last year I went to the museum in Vienna, to the Jewish Museum in Vienna, and I found that Pauli was also Austrian. I discovered that many famous physicists were Austrian. Can you tell us a little bit about your childhood and a little bit about the earlier history of your life before the US?
Yes, I'll be glad to. And let me pick up with these two names that you mentioned. These are two great physicists from the earlier part of this century, the first half of the century, Schrödinger and Pauli. And I have some direct, so to speak, connections with these two gentlemen. Schrödinger went to the same high school as I did, the so-called academic high school of Vienna. It graduated two very great physicists, Boltzmann and Schrödinger, whom you mentioned. And incidentally, I was there at my old high school just a few weeks ago, and I had a wonderful time. It's wonderful to see this new generation. My memories of that high school are very mixed. I had a very good education there for a number of years, but then in 1938, when Austria and Germany became one, I and all other Jewish children were expelled immediately within a matter of 2 or 3 weeks. So that's a rather bad memory. I was very glad to see when I returned recently that things have improved enormously.
Can you actually, going back a little bit to the scientific work, can you tell us a little bit, where was this conceived? I mean, of course, being from UCSD, I have to ask this question, as you realize. Where was this conceived? A little bit about how was this conceived? How does one think up a Nobel Prize winning idea? Maybe giving an advice to the younger people.
Okay. Where was it conceived? Absolutely clear cut. I was a faculty member here in San Diego, but I was on sabbatical leave in Paris. And Paris somehow lends itself to conception of ideas. I don't know what it is. There's certain magic to that city. How did that particular thing get started? Why not something totally different? Well, I happened to be working, and here's perhaps a little lesson to be learned, on a very applied problem. I was interested in alloys, electronic structure of alloys, and I discovered that metallurgists, theoretical metallurgists, had already for many years talked about this density of electrons in an alloy, how if you put, let's say, two different materials together in an alloy, the electrons may perhaps have a tendency to leave the one kind of atom and congregate on another kind of atom. But that was considered to be a very crude sort of description. And somehow, if I had more time, I could explain a little better, but in any case, I asked myself the question, in principle, does a description of electronic structure is a complete description of electronic structure possible in terms of this rather fuzzy notion of the electron density. So I wanted to see, are there some absolute limitations to this previously existing very crude notion, or can one make this theory absolutely precise? And then it turned out a rather simple demonstration showed that it could be made precise.
So then you came back to UCSD and you worked on it here?
That's correct. So I worked in France. I worked with a wonderful young man, an American, who was also on leave there by the name of Hohenberg. And in the meantime, I had already arranged for another wonderful then young man to work with me in San Diego. He is now a professor here, Professor Sham. And when I came back, he was already here, and we continued this work. And there are two papers, the first one written by Hohenberg and myself, and the second one by Sham and myself, that form the basis of this theory.
Now, you have worked on all these theoretical, kind of very heavily theoretical ideas. I have to ask you a little bit, you have had a whole parallel sort of a life, so far as I understand, working on more of on that administrative side of the universities. You worked here on the Academic Senate, I understand. You were the chairman of the Academic Senate. You also at Santa Barbara, you headed the Theoretical Institute in Santa Barbara. How can somebody balance all this? But I understand you have some political sort of activism, so to speak.
Yes. First to perhaps tell you how I see this picture. I see myself primarily as a practicing scientist and teacher, and only very secondarily as an administrator. I have not had major administrative responsibilities. Yes, I was department chairman here. I was chairman of the Senate here. And then in Santa Barbara, where I'm now residing, I started the National Science Foundation Institute for Theoretical Physics. The way you asked me how I balanced this, basically when I've accepted such administrative responsibilities, then I have always done it with my own understanding that I would give first priority to these administrative jobs, but I'd accept them only for a limited period of time. And during that time, I kept my scientific work going on a reduced level, but sufficient so that afterwards I could pick it up again.
So you mentioned that you think of yourself as a scientist, as a teacher. So maybe you can say a little bit about your teaching sort of interests and how, for instance, you have children, I understand, you have grandchildren. Does anybody pursue the career in science?
My grandchildren are too little to do that, although one of them, one granddaughter, seems to be very interested in science. Among my three daughters, they all started in the direction of the humanities, but one of them, at a certain point, after a sophomore year, just changed direction radically, and she is now a very capable and effective engineer. That's the one is my daughter Rosalind, who works with the State of California Water Department here in San Diego.
So since you mentioned that, maybe you can say a few words. What is the impact of this work that you have in more applied sort of problems? Because we talked about the scientific applications.
Yes.
Now the question is, does this have this purely theoretical sort of development, in some sense, has some applied implications?
Yes, indeed. I mean, the applied implications are multiplying very rapidly, and I'll just give a few examples. Generally, the examples involve, as I already mentioned, systems of very many atoms. Now, for applications where this technique has been successfully used, and when I say successfully, I can now, since we're talking about applications, put this in more, what should I say, ordinary terms. There are lots of people that are earning a good salary using this method. Catalysis or catalysts, development of catalysts.
Can you just say what catalysts are?
Yes, a catalyst is a molecule, or it can be a collection of atoms of some sort. In some cases, it's the surface of a metal that promotes or speeds up a chemical reaction.
For instance, what you have in a car.
For example, in a car. In a car, you have, as you know, the immediate result of the combustion that takes place in your combustion engine are a whole set of noxious gases, and everybody by law now has to have a catalyst as part of the car that converts these noxious gases into harmless things like water or carbon dioxide. Other applications, design of drugs. To find new drugs, traditionally one did an enormous number of exploratory experiments. Nowadays it's found to be more efficient to do an enormous number of quick calculations with density functional theory. Now, nobody would sell a drug on the basis of a calculation alone, but the calculations very often show the directions in which one will find better drugs.
What do you mean? How does one actually make a drug with a calculation?
Well, the calculation is kind of sort of in the computer. It's a virtual drug. You produce something in the computer that mirrors the real drug that eventually will be used by patients, and you can, through the computer, you can ask all kinds of questions. If this drug, for example, is put in contact with a cancer cell, what will it do? And you can work in this virtual reality of the computer with density functional theory, and it will save you millions of hours of experimentation.
Of making the actual drugs.
That's right.
And then have there been, do you have any example of a specific drug actually that you could mention?
Well, this is not, so to speak, my particular specialization, but I was at a meeting recently where a gentleman showed experimental drugs being tested by the NIH to be used in the fight against AIDS.
Mm-hmm. Now, since we're talking about science and what this could help us, maybe we could talk a little bit about the future.
Yes.
Where science is going in the future. Now, there is lots of one hears in the television, you know, lots of things about Bose-Einstein condensation, about teleportation, microstructures, all kind of words that, in fact, probably they don't mean much to many people. Can you give us sort of your vision of where do you think we're going, what's important, what directions, sort of general directions we should be going into?
Well, let me react to this question by quoting a very famous physicist of the earlier part of the century, a man by the name of Niels Bohr. Niels Bohr, by the way, I think I mentioned his name early in our interview. He had this model of the hydrogen atom with a nucleus and an electron going around it like a planet. I worked at his institute when I was a young man for a year or two.
In Copenhagen.
In Copenhagen, right. And there was a story attributed to him that he was asked a question like you're asking me, and he was a man who always thought for a very long time before he responded to anything. So he thought for a long time, and then he told the person who asked him, he said, you know, predictions are always extremely difficult, but particularly those that concern the future. And so that's my first answer to you. I think the use of history is a tricky business, and I think one shouldn't fall by any means into the trap of using history as a sure predictor of the future. But perhaps it is useful to ask oneself if, for example, 50 years ago, somebody had been interviewed, or I had been interviewed.
Well, that is the reason, actually, I'm asking you this question, because in 50 more years, we would like to look back at this tape.
Okay, well, that's, you see, it's for that reason that I'm very cautious here, because if anybody now looks at predictions made 50 years ago, what would happen in the year 2000, they would all be found to be completely wrong. So it is not possible to really count on making predictions that will be reasonably sure to become true. Nevertheless, I think talking about predicting the future is a useful exercise because it raises all kinds of questions, and progress is made through questions and answers. So I think asking the question is fine. Expecting an answer that will be true is not fine.
So do you have perhaps any kind of more general ideas that you can give us? Do you think, we should concentrate, at least in a short period of time, let's say? What's the direction in the short? Because definitely scientific policy is even done that way, that one kind of tries to predict where the important developments will come from.
Yes.
So is there any kind of maybe short, not on the 50-year time scale, but maybe on the 5-year time scale, which direction we should be pushing?
Yes.
Does your work, for instance, I presume, has importance in pushing in a certain direction?
All right. Well, that, you see, makes it a little easier for me because, of course, I know my own area much better than science in general. Now, in my own area, there has already just picked up this new activity of predicting chemical processes, predicting the properties of new chemicals in a computer. And that's something that really wasn't possible until quite recently. And you can see easily that trying to predict properties of materials, I've mentioned drugs, that's an open-ended thing that has enormous possibilities in the future. And I certainly can say with some confidence, because that's a very short-range prediction, that that's going to accelerate.
Well, unfortunately, our time has come up. Thank you, Professor Kohn, for joining us. And of course, you are always welcome to your house at UCSD.